Hello everyone, I hope you're doing well. We're well into week 2 of our distance learning, and we had a leadership team meeting yesterday, and there are a few pieces of information I'll like to pass along. Number one, in the meeting we discussed the idea of trying to standardize some of the instruction. So all of your teachers, with very few exceptions, should be using Google Classroom, Remind, and we're also going to start using Zoom at least once a week. I will coordinate with some of the other teachers. They've got a schedule we're looking at, and I will send out information to you as soon as I have that. But suffice it to say, I will be having a once a week Zoom meeting with you to answer questions, go over anything that you might have concerns about. But we'll have a set time each week. I may have 2. Again, it just depends on how the schedule pans out. But you can look for that in the very near future. Hello everybody, we're going to start talking today about friction. Please be careful to pay close attention to the examples. Friction's not difficult, you can do it, but friction can be a little bit confusing. So just be careful about paying close attention, especially to the example problems. Friction is exactly what you'd expect it to be. It's a resistance to motion. Typical examples would be sliding a box across the floor, air resistance, which we actually won't do any calculations on, and rolling resistance, which we won't do any calculations on either. We're going to be focusing on problems that involve things like sliding an object or a box across the floor. If you can understand that, then later on when you go to college, you run into these other things, you won't have any problems with them. Don't forget weight and normal force. It's real quick here, just as a reminder, weight, as we know, goes this way, and weight equals mass times gravity. And the normal force, which is the one that's going to matter in friction calculations, is the force that pushes back up. So if I have an object sitting here, it pushes down on the ground with a weight that's equal to mass times gravity. That, of course, is going to be a negative number. And the normal force is going to be the exact same magnitude, so it's like the absolute value of mass times gravity. Super important. Normal force, that pressing back up from the ground back up on an object, is what we use when we do friction calculations. 2 different types of friction, and this is where you've got to be careful. They use the exact same formula. The only difference is we talk about sliding friction, we're talking about an object that is already in motion, and then in a moment we're going to talk about static friction. So for sliding friction, key ideas are, number 1, if the motion is going to the right, the friction force is obviously going to the left. It always opposes motion, and it's always parallel to the surface. This is the one that causes people some confusion. It is independent of the area of contact. We're going to come up with a thing here in just a few minutes. We're going to introduce this idea of coefficient of friction. The coefficient of friction depends on the 2 surfaces, not how big they are. If I have a tarp that's a 10 by 10 tarp and I'm pulling it across the ground, there's going to be a coefficient of friction between the tarp and the ground. If I make the tarp 100 by 100, it's a huge tarp. Now, the reason it's harder to pull is not that the coefficient of friction changed, it's that the tarp is bigger, it's more massive. So keep in mind that the friction between 2 things, the coefficient of friction, the way the friction works does not matter on how big it is, it just matters on the surfaces in contact. So if we have an object at rest, we have static friction. We have an object in motion, we have kinetic friction. So when we're talking about something that is sliding, we are talking about kinetic friction. Now for static friction, that is an object that is sitting still. So if I have like this example here of the garbage can, if this garbage can is sitting still, it doesn't just start moving around on its own. If I apply a very small force to the side of it, I'm pushing it right here with a small force, unless that force is greater than the static friction, the garbage can is never going to move. So a static friction by definition is the force that keeps an object at rest. This little thing right here, this symbol is mu, Greek alphabet mu. So we say the static friction is less than or equal to mu s, which means static, the coefficient of static friction, times n. Now n, normally we'll write that as Fn for a normal force, because that is actually a force there. So this, again, don't get super freaked out. This is not the standard way we'll see the formula. but just know that that is the basic setup of the formula. We'll get to the formulas here in just a moment. Okay, let's talk just a little bit about static friction. So I've got a board here, and I've got beaker. And when I put beaker on the board, obviously beaker is not going anywhere because there's no force acting on him, but I can make a force act on him without even pushing him by raising the board a little bit. Now, right now, beaker's going nowhere, but what's going to happen as I go higher with beaker is eventually I'm going to reach a point, as you can see, beaker's starting to move, and the higher I go, the more likely it is that beaker will move down the board. Well, what's happening there? Well, what's happening there is pretty simple. Take a look at our picture here. So we've got beaker represented by the little red dot, and as this angle theta increases, the applied force, which is the force going, now let me back up just a second. The weight of beaker doesn't ever change, but the normal force, which is perpendicular to the surface, the normal force is always perpendicular to the surface. The normal force varies slightly, and the normal force, as it goes up, I go from having normal force and weight in perfect balance here. The normal force actually goes down because part of that force gets transferred into down the slope. Now we're going to have a separate lesson on this whole idea of going down a slope or being on an angle, but just you can understand how that works just pretty much just because how you live your life. You understand as this goes up, the amount of press into the board goes down even though the weight remains the same, and there's some force moving down the hill. What happens is at a certain height, depending on the coefficient of friction here, the applied force, which is the force pulling him down the slope, is greater than the friction force holding him back, and that's what allows him to start sliding down the hill. So we start thinking about this idea of static friction. It is this force that's holding him in place, and you can see at a low angle, he didn't go anywhere because the static friction was high enough to hold him in place. The force going down the hill at a low angle was less than the friction force holding him in place. But as we got higher and higher and higher, the applied force finally got large enough and the friction force remained the same because friction force is dependent upon the object and the surface that it's on. So as I change the angle here, as I was changing the angle, once I reached the point of no return, he will start sliding, and he would continue sliding at that angle regardless. Let's start talking a little bit about kinetic friction. Now, kinetic friction means the friction of motion. Formula is basically the same thing. We're going to change this up in just a moment anyway, so don't even worry about writing that one down. We're going to get different formulas in a moment. But what you need to get on this is the idea that the coefficient of kinetic friction is always less than the coefficient of static friction. So again, take a look at the garbage can here. If the garbage can is sitting still, to make it move takes more force than it does to keep it moving. It's exactly how you've experienced in your life. If you've got to move something heavy and you push on it, it's always harder to get it started than it is to keep it moving. And that's because the coefficient of static friction is always greater than the coefficient of kinetic friction. Now, these are your formulas. This is just a basic formula that says that the net force acting on an object is always the applied force minus the friction force. So if I'm pushing this way, that's my applied force, then the friction force is in opposition, and my net force, which is the only one that goes into force equals mass times acceleration. When I do force equals mass times acceleration, I have to remember that the only force I can use here is my net force. So net force equals mass times acceleration if you consider friction. Friction's involved. Now this is the friction formula. So friction force equals mu times normal force. Friction force, which is what we're getting right here, this friction force, right? Ooh, friction force. Friction force is mu times normal force. Mu, again, is the coefficient of friction. Coefficient of friction can be static friction or kinetic friction, depending on the problem. Just know that once you calculate mu for two surfaces, it's always the same. And this is just a reminder that weight equals basically absolute value of weight, I guess I should say, equals the normal force, which is Fn, and that is m times g. M times g. These are the formulas that you need. These are the formulas you need to write down. So if you have not already jotted these down someplace, pause the video for a second, write down these three formulas. You're going to need them, and you might want to even add a little note here that the net force equals mass times acceleration, which is you're going to need that to calculate how fast something is moving depending on how hard you're pushing on it. So pause it for a second, write down those formulas, and then start it back up. To end this video, we're going to take a look at example problem number 1. We have two masses. Mass number 1 up here on the table, and it is 10 kilograms. And mass number 2, which is hanging here. Now we're going to assume this is a frictionless, there was no friction on the pulley itself. So we kind of ignore the pulley for right now. The only friction is between mass number 1 and the table. There is friction here, but there's no friction in the pulley itself. I have mass number 1, which is 10 kilograms, and mass number 2, which is 5 kilograms. Now you know, just from being a person, that if this was like ice and the coefficient of friction was super low, of a weight of 5 kilograms and a mass of 10, this would cause this to slide across the table. Well, in problem part A, it's asking you what coefficient of static friction would stop the block from sliding. And in part B, we know if the box is sliding and the coefficient of kinetic friction is 0.2, what's the acceleration? So we're going to look at these two parts, A and B separately. Make sure you understand these. These are what I would consider to be a very classic friction example problem. The sort of thing you would expect to see, on a test, or, as you go to college, you'll see these sort of things when you get there. So for example 1, just a quick reminder, we have a box here, 10 kilograms. We have a box here, 5 kilograms. And we want to know what mu static friction would be if it's not moving. So what we do first is we need to find the normal force for 1. So we're going to find the normal force for this one. And we need to find the weight for this one, because we need the normal force to calculate the amount of friction, and we need the weight to calculate the amount of applied force. So for Fn for M1 is 98 newtons, and the weight for M2 is 49 newtons. For both of those, we just took Fn equals M times G, so we took 10 times 9.8, and 5 times 9.8 give us those two answers. Now we know that the weight is the applied force because that's the only force pushing down, which means that's the amount pulling on the box. So if we've got a downward force of 49 newtons across the pulley here, that's how much 49 newtons is pulling on the box, which is the applied force. Since the box is not moving, the applied force and the friction force must be in balance. Just think of it like this. The applied force of 49 newtons, it's not moving, so the force of friction, so I have an applied force here, and my friction force must also be 49 newtons because it's in balance. It's in balance. So we're going to use friction force. I need to get rid of that. We're going to use, I'll read right here. Friction force equals mu times normal force to find mu. Go to the next slide here. So we're going to use friction force times mu equals normal force. From the previous page, we know that the friction force is 49 newtons. The normal force is 98 newtons. Divide 49 by 98, and we end up with an answer of mu of 0.5. So mu, and we should put a little s on there if we want to be very specific, equals 0.5, and that is the answer to problem number A. If you need to back it up and look at it again, it's a really straightforward problem once you see it worked out. Take a look at that again and then move on to part B. So for part B, we have the same basic setup. We got 10 kilograms up here. We got 5 kilograms down here. But in this case, the box is moving with a coefficient of kinetic friction of 0.2. And we want to know how much is it accelerating. Well, just keep in mind before we even get started that if I've got an applied force here and a smaller friction force, that's what it's going to require for it to stop, then the force that I use to calculate the acceleration is the net force. And the net force equals the applied force minus the friction force. So that's where we're headed. Once we're going to get the applied force, calculate the friction force, and then we get the net force. Once we have the net force, we can use force equals mass times acceleration to calculate the acceleration. So we already have that the normal force for M1 is 98. We already have that the applied force for M2 is 49. And so we use friction force equals mu times normal force. Now keep in mind, it's not balanced this time. So FA does not equal FF in this case because the object is moving. In part A, FA equaled FF because it was sitting still. So this does not hold true for this one. We have to calculate the friction force now. So we substitute in. Friction force equals 0.2. I take my coefficient of friction, substitute it in, times 98 newtons. That gives me a friction force of 19.6 newtons. So net force is applied force minus friction force. The applied force is still 49. That's how much this is pushing down, 49 newtons, which means that's how much it's pulling across here, 49 newtons. Minus the friction force gives me a net force of 29.4 newtons. We'll just take that 29.4, substitute it into this formula, and we're done. We found the acceleration. So on to the next slide here. So the net force is, again, this is just a reminder, 29.4. Force equals mass times acceleration. Substitute in 29.4, the net force. Be careful when you're doing friction problems, always use the net force. Equals 10 times A. A ends up being, we take 29.4 divided by 10, gives me 2.94 meters per second, which is 2.94 meters per second squared, if you want to write it that way. And that is the answer to problem number B. Okay, that's going to be the end of the part 1 video. We will pick up with another example problem in the part 2 video.